In this video, I would like to discuss with you what is the influence of the driver inputs on the car balance, and when you have balance issues, is it coming from the driver or is it coming from the setup? Hello, this is Bruno. I'm the lead performance engineer at Optimum-G. So, vehicle balance is a function of, typically when we are at the racetrack, we're more focused on the vehicle setup. But we have to remember that the vehicle balance is also a function of the vehicle design, naturally. It is also a function of track conditions and tires. So as the track or the tire conditions are changing, it's gonna influence the vehicle balance. Then on top of that, we have the vehicle setup that we're typically discussing. Not only all these items and many others, we always have to keep in mind that the vehicle balance is heavily dependent on driver inputs. And this is the focus of this video. How is the driver inputs influencing the balance that we see on our car? So we are going to first analyze how the brake input is influencing the balance and then how the throttle input is influencing the balance. So in this case, let's assume a given corner. So here we can see the speed trace. Let's look at two different drivers. We have the brake trace, the brake pressure trace of driver number 1. And then that is not trail braking a lot, meaning it's not carrying the brakes really deep into the corner, it's not combining much the brakes and the steering. And then we have driver number 2, which is trail braking a lot more. So we can see that the driver is carrying the brakes further into the corner and combining more the steering with the brakes. So if we analyze this specific point here at corner entry, we can try and understand which one should have more oversteer or more understeer because of different brake application. All of this is answered mostly by weight transfer. So in the first scenario, we have some longitudinal acceleration or some deceleration because there is a little bit of the brakes applied, but not a lot, meaning that when we transfer the weight because of the brakes, we have more load on the front and less on the rear. However, the split is not really big between the two axles. Now we want to look at frictional ellipse of the tire, of the rear axle and the front axle. Quick reminder, frictional ellipse is going to be showing the longitudinal force capabilities and versus the lateral force capabilities. So this is what we're going to have for the baseline braking. It is going to be on the rear, lower force because you are decreasing the vertical load, which decreases the size of the frictional ellipse, while on the front it is a little bit larger because we are loading the front a little bit. We can see that as we brake, we are saturating the tires a little bit with longitudinal force, as we can see here. However, we are trying to exploit the tires at the highest lateral forces when we are cornering. Now, for the second scenario, the driver is holding the brakes a lot longer and applying more pressure at the corner entry. What does this mean? It means that the longitudinal deceleration is higher and that the driver is loading the front axle more and unloading the rear axle more. Now, if we look at the new frictional ellipse that the front and rear would have, on the rear we have a smaller frictional ellipse. Why? Because the vertical load is lower, meaning the lateral or longitudinal capabilities of the tires are lower. And on the front axle, we are actually increasing the grip available because with higher vertical load, we have a larger frictional ellipse and we can generate more lateral force. So yes, even though we are braking more and using a little bit more of the tire longitudinal force, we can see, and saturating the tire even a little bit, we can see that the increase of lateral force from this added vertical load is even more influential. So by carrying the brakes further into the corner, we are increasing the lateral force on the front axle, decreasing on the rear. In terms of balance, this means that the car is more oversteer. The front is more pointy and it's rotating the car more, and the rear is not generating as much force. So we can see that in the second scenario, we should be expecting a more oversteering car. Now, another example of this, we were discussing trail braking here. Another example would be throughout, let's say, a long corner, in which we have, in this case, we have a reference neutral steer for this corner here. If we look at scenario number 1, the driver is applying the brakes, releasing, entering the corners, and never touching the brakes again. Let's say that the same driver, after a few laps, starts getting more understeer because of tire wear. What could be the driver doing, and this is important, to adjust vehicle balance during a race? One of the few things that the driver can do, and is actually very influential, is changing its inputs. So in scenario number 1, the car is having the understeer. This is why we see higher steering compared to the neutral balance. Now for scenario number 2, the driver is also applying a little bit the brakes later in the corner. Let's say that it's a second apex, very understeery car. The driver is applying a little bit more the brakes. What should we expect? We have higher deceleration. The car is braking a little bit, transferring a little bit of load to the front axle and removing load from the rear axle. So as we can see, a little bit more loaded front axle. What this would be doing, as we saw, it would be expanding the lateral force capabilities of the front axle and helping to cure a little bit of this understeering car. So we would have more force on the front, helping to rotate the car, and the driver would need less steering. We know that typically less steering is indicating less understeer, and we actually have a full video explaining why that is the case and how we should be looking at steering profiles to characterize vehicle balance. But it's interesting to see how the driver was able to change its inputs to solve a little bit of the issues that he or she was having during a race. So in summary, as we apply the brakes, we just saw that we should be expecting more oversteer. So applying more of the brakes, we go to the more oversteering direction, or carrying more the brakes, we would have more oversteer at corner entry. Up to a point, because your brake bias is going to be naturally a lot higher, a lot more to the front, meaning that at a given point, if you carry too much of brakes or if you apply too much pressure, you're going to lock the front axle. So even though you were generating more and more oversteer, when you start saturating the front axle or even locking the front axle, you're gonna get understeer because the front tire cannot generate as much lateral force anymore. So we can see that now, after we have the front tires locking, either both or the inside tire, you start getting more understeer. We can see this more linear region going towards oversteer, and then we have a change of direction. And how can we influence how much oversteer we get from touching the brakes or carrying the brakes? By changing the brake bias, you're going to be influencing this. So let's say that we move the brake bias, we shift it forward. This means that, let's say that the deceleration is the same. When you move your brake bias forward for the same deceleration, you're saturating a little bit more your front tires with longitudinal force, meaning that you are slightly decreasing the lateral force capabilities of the tire. So this means that as you apply the brakes with a more forward brake bias, you are not getting as much oversteer anymore because you are saturating the front axle a little more than in the baseline case. But you are still locking the front tires and then getting understeer past a point. Now, if you move the brake bias rearward, you're gonna be saturating the rear tires more, meaning that when you are steering and entering the corner, your front axle is gonna have a lot of lateral force available to be used, while on the rear, you are decreasing a little bit. This means that you're actually getting even more oversteer than you would otherwise. And even more interesting is that now the tire that is going to be locking is going to be the rear tires. So once you start saturating the tires, you would get to an oversteering behavior. This strategy can be used with race cars that are naturally extremely understeery. So by moving the brake bias rearward, you're gonna be getting more oversteer or less understeer in this case as you enter the corner and trail brake, and even to the point that sometimes you're locking the inside tire, which is gonna help fix this high understeering car. The disadvantage of this is that you are going to lose longitudinal capabilities. So if you move your brake bias outside the ideal value for maximum braking straight line performance, you can be fixing somewhat your balance, but you're going to be compromising braking capabilities. Now we can look at the throttle influence. So again, we're looking at a typical corner and we're going to focus on the corner exit. In the scenario number 1, the driver is only starting to apply the throttle very late in the corner exit, while the second driver for the same car is applying the throttle a lot earlier. And again, let's look at the phase in which the throttle application is different between both drivers at corner exit. One of the drivers is going to have more understeer, the other one is going to have more oversteer. And again, it is mostly explained by weight transfer. In this case here, in the first case, in blue, we have a small longitudinal acceleration, meaning that we are loading just a little bit the rear tires and removing load from the front tires. What can we see in the friction ellipses? We can see this reference, a little bit higher force on the rear compared to the front. Now, if we look to the second driver in red, it is applying more the accelerator, the throttle, and we can see that the longitudinal acceleration is higher. This means that you are transferring more of the load to the rear axle and decreasing even further the load on the front axle. When we look at the friction ellipse, what should we see? We are gonna see an expanded friction ellipse for the rear tires, because by increasing the vertical load, you increase its force, its grip capabilities. And on the front, you're gonna see a smaller friction ellipse because you decrease the vertical load. So it's interesting to see that even though you are using more of the longitudinal force of the tire and slightly saturating it longitudinally, you still have higher lateral forces over here, while on the front you have lower lateral forces. If you increase the forces on the rear and decreased on the front, you're getting a more understeering car. So here, as you apply the throttle, you're gonna get more understeer, typically. So this is a corner exit scenario. If we look at the different scenario, it's not when the driver is applying the throttle, but it's when the driver is actually lifting the throttle for a corner. Let's use this very high speed corner or a kink as shown here. And one of the drivers is gonna do it full throttle. So in this is the apex of the corner, he's not lifting anything, he's able to carry that speed. This is gonna transfer or keep the load on the rear axle, because with higher longitudinal acceleration, it's gonna transfer more load to the rear, helping the rear actually, it's giving the rear higher grip and more stability to the car in general. This is gonna be the steering profile. So this, let's assume it's a neutral balance. Now in the second scenario, the driver is lifting the throttle. We need to understand when he's lifting the throttle, it's not only about decreasing the speed there, it's gonna actually influence the balance of the car in that section. So by releasing the throttle, it's gonna decrease the longitudinal acceleration of the car. So instead of transferring a lot of load to the rear, it's actually now just transferring a little bit. And by doing that, we have higher force on the front than on the rear than we had in the reference case. This means that we are increasing the force on the front and decreasing the force on the rear, or the grip available on the front and on the rear. What does this mean? It means that we are gonna have a more oversteering car by lifting the throttle in general. So in this case, it was what happened, and the steering profile, it's gonna look more like this. Once the driver is releasing the throttle, we can see the driver applying corrections on the steering wheel as a consequence of that. We have to understand that when the driver is lifting, it's changing the speed, but also the balance of the car. If the limit here was just the balance, maybe more throttle would actually help. If the issue was really carrying too much speed, then obviously releasing the throttle or lifting the throttle would be the solution to that. So for the throttle, in summary, as we apply more the throttle, we are gonna go more on the understeering direction up to a point, because as we apply the throttle, we are loading the rear, But at some point, if we have a lot of power or if it's a low speed corner, we are going to saturate the rear tires. Once we saturate the rear tires, it cannot generate lateral grip anymore, and you have a more oversteering behavior. This for a rear wheel drive car. For a front wheel drive car, you're gonna get, as you apply the throttle, you're gonna get even more understeer, because not only you have the weight transfer generating understeer, but you are also saturating the front tires with longitudinal grip. So you have even more understeer, and when you completely saturate the front tires and you get some tire spin, you're gonna actually go in the understeering direction because your front axle cannot generate lateral force anymore. Now let's look at a few examples of throttle understeer and then throttle oversteer. In this case, we have the reference lap shown in black and then the comparison lap shown in red. So we can see that the comparison driver is trying to apply the throttle a lot earlier to try and get more exit speed. However, this extra throttle is inducing some understeer, so we can see the higher steering here indicating understeer. Because of this higher understeer induced exactly by the driver input trying to go too early or too soon on the throttle, he needs to lift the throttle, and by lifting the throttle here, he's losing a lot of speed. So when you look at the exit speed, even though it was carrying more speed initially because of this throttle, then it's losing all that speed because of this lift. And it's just important to understand, because the driver is going to be reporting understeer on throttle, and it's important for you to understand, is it coming from the driver or is it coming from the setup? And we're going to discuss this in a little bit. In this other example, we have the opposite. So the comparison driver in red is carrying too much speed and inducing some understeer at the entry. So probably he didn't get the car rotated enough at the entry and apex. When he or she goes back to power, the throttle application is inducing oversteer, because probably the rear axle was still generating lateral force, it was not on a straight line. The driver saturates the rear tires, for example in a low speed corner, and then you can see big steering corrections being applied. So even though the steering profile was supposed to be always positive for this corner, like you have for the reference lap, you can see very high steering corrections for the driver applying the throttle. So in this case, we can see how the throttle saturated the rear tires and actually caused oversteer. Now, it is just interesting to put together brakes and throttle so that we can see that they go in opposite directions. So for the brakes, as you apply the brakes, you're gonna get more oversteer up to a point where you start locking the front tires, while for the throttle, as you apply the throttle, you are getting more understeer up to a point where you can get either more understeer if it's front wheel drive or oversteer if it is rear wheel drive. Okay, so now it's clear for us that it's not only a matter of vehicle setup influencing the balance of the car, but it is also a matter of driver inputs. And the question is, how do we know when it's setup? How do we know when it's driving technique? And this is what we're gonna cover now. All right, so is it setup or is it driving? What is our goal when trying to maximize car and driver? Our goal is to carry as much speed as possible, given the available grip of the tires, car, and track. And how do we do that? By exploiting the friction ellipse of the tire entirely for each phase of the corner. So we want to explore all the braking, all combined grip, and all lateral grip. Okay, so let's start with an ideal setup. We have the speed profile, this is the theoretical speed profile that is coming from the whole available grip of the tire. For the ideal setup and driving, we would be exploiting all of this available grip and carrying as much speed as possible. Now, in the non-ideal setup and driving, it could be a setup issue, it could be a driving issue. We are not going to be exploiting the friction ellipse at the limit and therefore not carrying as much speed as possible. So we can see here that we are losing speed on braking and then losing speed on corner exit. Now let's look from the from the tire perspective, so here again we have the friction ellipse of the two cases. We have the case on the left of the ideal setup and driver, and on the right of the non-ideal setup and driver. So for the ideal scenario, the driver would be braking at the car maximum potential. Why he or she is able to do that? Both because they are exploiting it by applying enough of the brake or applying enough the brakes, but also because the car gives you enough stability to do so. Then the driver is gonna transition into corner entry. He's gonna carry as much as the brakes as he can, while exploiting and using the steering to explore the combined acceleration or combined force available from the tire. Again, why are they able to do that? Both because they are using proper technique and trail braking enough, but also because the car setup gives them enough stability, not too much oversteer, enough response. So the setup is also allowing them to do that. They go to the apex where they exploit the full grip available because the car balance is neutral. Corner exit, they can go back to the throttle without too much oversteer or understeer. And then they finish the corner. Now, on the non-ideal scenario, the driver is gonna brake, but not exploit the full braking capabilities of the car. It could be, for example, because the car is moving, it's not stable enough, or it could be simply because the driver is not applying enough the brakes. And you start seeing how driver feedback starts connecting, because if the driver is reporting this instability, we can understand if it's a driver issue or if it is a setup issue. Now, when we go to the corner entry, the driver cannot trail brake as much in this case, let's say, either because he's not simply carrying enough the brakes to exploit this combined grip, or because the car is too oversteer. If the car is too oversteer, he cannot keep the brakes because, as we just saw, it would induce even more oversteer. He goes to the apex, he's exploiting quite a high grip, but not everything, because the car is a little bit understeer or a little bit oversteer, let's say. And then corner exit, he tries to go back on power. Either he's not exploiting the full grip capability, or the car is too oversteer or understeer for that to happen. So in this case, we can see that each of these phases that the driver did not exploit the full capabilities of the tire, it could be because of a balance issue, or it could be because the driver is simply not at the limit. Okay, so now we have it very clear that vehicle balance is a function at the same time of vehicle setup and driver inputs. And we can see that actually this is a system. And then the question is, if they are both influencing the vehicle balance, how do I come to an ideal setup? How do I find this setup? So let's discuss the responsibilities of the driver and of the engineer. First, with the driver, what should be the driver doing? The driver should be exploiting the current limit of the car and making sure he identifies any issues with car balance. And then on top of that, he should be communicating this information to the engineer. On the engineer side, he should be first helping the driver to exploit the current limit by analyzing data and video with them. And again, we have a separate video on how to do that. And then second, also making setup changes to expand this current limit and to allow the driver to exploit this limit. So here we can see that both of them are working together. There is an iteration that we are both working with the driver to make sure that he exploits the limit, and the driver making setup changes to allow the driver to exploit this limit or even expand the limit of the car. In summary, we saw how driver inputs is gonna be influencing the balance of the car, how the brake and the throttle is gonna influence understeer or oversteer directions. And then we also understood how do we know when it's a driving issue or when it's a vehicle setup issue, and how we should be working with both of them to extract the ideal setup and ideal car performance from both the driver and the car. If you like this content, you would love our seminars. First, we have the data-driven performance engineering seminar. In this seminar focused on performance engineering, we are discussing for 3 or 4 days, 11 hours per day, everything related to performance engineering. So we are analyzing drivers, everything that we saw here in more depth, but data analysis in general, vehicle setup, tires, and how to connect all of them. We teach dozens of techniques for data analysis and for performance engineering, also with exercises. So we are practicing all the techniques that we teach to make sure that you can also use it with your car. Besides that, we show hundreds of real examples so you can see how you can apply each of the techniques taught. Now, for the Applied Vehicle Dynamics seminar, it is a very important seminar because you understand all the foundations that we discuss here. So, for example, weight transfer, kinematics, tire friction lips that we were speaking about, tire grip, tire temperature, and how you can connect all the different areas of your car to better understand it and to better extract performance from your car. If you're interested, you're gonna find our calendar in the description of the video, and you can also send us an emails should you have any questions about the seminars. If you think that your team or your company can benefit from working with us, these are the services that we offer. Performance engineering, where you could have one of our performance or race engineers at the track with you, using all of the tools that we use ourselves at the track. We also do vehicle dynamics consulting, where we help with car design, tire designer selection, vehicle benchmarking, simulation, and everything related to vehicle dynamics. Also, we offer simulation software. So we have pieces of software for vehicle dynamics, tires, and kinematics. If you're interested to know more, you can see all these activities in our website, or you can reach out if you think that we could be a good fit at engineering@optimundi.com. Thank you very much for watching the video. If you have any questions, leave them in the comment section, and I'll see you in the next one.